welcome back to this course. So, today we will extend the concept of Fourier series. So, today we are going to start with the lecture 19. So, in the last class I have discussed about that when the function f x is a periodic function having a period from minus L to L, then this can be written as a Fourier series a naught plus summation n from 1 to infinity a n cos n pi x by L plus b n sin n pi x by L, where my x belongs to minus L to L, and this function is a periodic function with x plus 2L is equal to f x. Now, today I will discuss that what are the convergence of Fourier series. So, what are the conditions? So, in this case, so let my f x be piecewise continuous on minus L to L, and so what is the meaning of piecewise? That is, the f x is defined and continuous for all value of x belongs to open interval minus L to L, except at finite number of points. So, the function is continuous except at the finite number of points. Then the second one is that at any point x naught belongs to the interval minus L to L, because this is an interior point I am talking about, where f x is not continuous both the one sided limits, that is the limit x tends to x naught negative f x and limit x naught positive f x should exist and are finite. Okay. So, and the third one is that the one sided limit, that is limit x tends to L positive f x and limit x tends to L negative exist. So, from here, because my interval is from minus L to L, so it is minus L and this is plus L, exist and are finite. It means that suppose I have any function so let my take a function f x which is of this form. So, this is my x axis, this is my y axis, and suppose my function is, so this is minus L and this is plus L. So, suppose from here my function is like this to this and then from here my function is this one, and then from here I have a function that is this one. So, what I say that from this condition that this function is a piecewise continuous function, it is continuous from here to here, from here to here, from here to here, and it says that at any point x naught between these, if the function is not continuous both, so like this point, so both the one sided limit. So, from here the if I take the left hand limit for this function and right hand limit for this function, left hand limit for this function at this point and right hand limit at this point should exist and should be finite. So, from here you can see that this has a jump discontinuity, you have a jump discontinuity, and also that the one sided limit of this function. So, here from right hand side I want to go, and from here I should go from the left hand side. So, this limit should exist, only then we will say that this is the condition, it is called the piecewise continuous function. So, now, so suppose this function is there. Now, if, so this is the statement of the theorem, I am going to use now that let f x and f dash x be piecewise continuous on the interval minus L to L, then the Fourier series of the function f x on this interval converges to the function f x at a point of continuity now. What about at the point of discontinuity? The Fourier series converges, the Fourier series converges to the average, the function f at x plus so because this is the point of discontinuity at x. So, what I will do, I will find out the left hand limit, right hand limit, and then taking the average. So, in that case the function, the Fourier series will converge to this value. So, this is the statement of the Fourier series or the convergence of the Fourier series. So, no, at this moment we are not going to do the proof of this one, but this statement we just take as a statement for the convergence of the Fourier series. Now, we want to put some remarks. So, remarks is that the first one is that at the end points, so at the end points in the interval the Fourier series converges to half f minus L plus So, this will be the both the endpoints. And the second one is that now I have the Fourier series. So, my Fourier series is f x is equal to a 0 plus summation a n cos n pi x by L plus b n sin n pi x by L. So, in this case, if you see that if I put x is equal to minus L, so what I will get f is equal to minus L n from 1 to infinity a n. So, cos minus L will be cos L. So, it will be n pi L by x n pi L by L. So, this will cancel out, this will cancel out. So, from here I will get a 0 plus a n cos n pi. So, because this L and this L will cancel out, and this is sin n pi. So, for any value of n, this value will be 0. So, I will left with only this value. And similarly, if I want to find the value of at L, then if you will see this one, you will get the same value a 0 plus summation a n cos n pi. So, in that case I can say that, so from here I can say that, so this is my remark number 2, that the series converges to the same number at x is equal to minus L and plus L. Okay. So, it means the series converges to the same number, because I am putting L is equal to minus x is equal to minus L and plus L, I am getting the same value of the function. So, this is the observation. Now, so once I am able to find the Fourier series, and then if my function is satisfying the conditions, then I can say that my series is convergent. So, let us go further and use some properties of the function to find out the Fourier series. So, now I have my Fourier series a 0 plus this one cos n pi x by L plus b n sin n pi x by L. Now, so this is, I just take one. Now, the condition, so now suppose I have a function f x for the x belongs to minus L to L. So, the case 1 is that I found that my function f x is an odd function. Odd function means I am getting that f of minus x becomes, so this is my odd function. So, in that case, if somebody asks me to find out the Fourier series for this function, that function is an odd function, then there is no need to find all the coefficients, and then we found that this is the Fourier series. Just before starting with the Fourier series, we can say that if my function f x is an odd function, then you know that my a naught is a function of, has a value from this to this. So, this is the odd function, and I am integrating the odd function from minus L to L. So, I know that this value will be 0 by the properties of the integral, that I am, odd function means this type of function, like whatever the function I have on the left hand side, suppose this is my L and this is capital L. So, suppose I have a function of this type. So, on the other side I also have the function of this type. So, this area and this area will cancel out and we will get the value 0. My a n will be cos n pi x by L dx, and from here also you can say that my function is odd function. Cos function I know that is the even function. So, product will be the odd function, and in that case also this value will be 0. So, for the odd function my a0 and a n will be 0 and my b n will be 1 over L from minus L to L f x sin n pi x by L dx. Now, I have a odd function, f x is odd function, sin is odd function, and odd function to multiply the odd function is the even function. So, in this case this will be the even function, and then I will apply the properties of the even function, that is 2 by L from 0 to L, it will be f x sin n pi x by L dx. So, I am only left with b n which is not equal to 0. So, from here if I want to write the Fourier series of function which is an odd function, then you will see that I will come up with only n from 1 to infinity, that is my b n sin n pi x by L. So, this is my Fourier series, because this is the odd function, and on the right hand side also sine function is the odd function. So, I know that the equality, the left and the right should be of same type, because this is odd function, then it should also be 4. So, this is the corresponding Fourier series for the odd function. Similarly, I can go with the function f x is a even function. So, whenever the even function, this is my even function, and if you see the picture of the even function, that suppose this is minus L, this is plus L. Suppose I have a function from here, it is of this type, then even means on the other side it is just the reflection about the y axis. So, in this case you will see that this area and this area, if I integrate, this is the area and that cannot be 0. So, this is my even function. So, now in that case I want to write the Fourier series. So, left hand side is the even function, it means from my knowledge that I can find that on the right hand side it should be always even. So, you can see from here that in that case my b n will be 0. So, a n will be remain like that one, because a n is a 0 is 2 by L So, this part will be always, I will use the property of even function. So, it is from 0 to L f x dx. So, this will be the value of a 0. Similarly, my a n will be dx f x into cos n pi x by L dx. So, this is a even function, this is a even function, that is a even function, and then I have used the property of the even function to find out the integration. So, this will be able to find out this one, and you will see that my b n in that case will be 0. So, in that case I will left with only the values, the coefficient of cos terms. So, from here I can find the Fourier series. My f x will be a 0 plus summation a n cos n pi x by L, where my a n and b n is given like this one. So, this is that if I have some function and I have the knowledge about that function, that whether this function is a even function or odd function, then I can apply this formula directly. So, from this one I will going to start with the cosine series and the sine series. So, let us start with the new way of doing the series is Fourier half range series. So, what is this Fourier half range series? Actually, when started with the Fourier series, we know that I have a function f x and my x belongs from minus L to L. The only thing is that suppose I do not know the function, I have a function whose value the x, the value of the function is given to me only between 0 to L. So, instead of this function of this form, now I have a function f x such that x belongs to 0 to L. Actually, if you see in general cases, always whenever we define a function, the function is given to us when the x lying from 0 to some finite value. So, in that interval we have the value of the function. So, this in this case I do not know what is the value of the function from minus L to 0. So, now if somebody asks me to find out the Fourier series, then I know the value of the function only in the interval from 0 to L, and I have no knowledge about the function from minus L to 0. So, if I want to apply the Fourier series, I am unable to do that, because in the Fourier series we have started with that the function is a periodic function and it has a period 2L and defining from minus L to L. So, what we will do in this case? So, in this case we will take the help of that the case 1 I will take. So, in this case I have the function f x, this is given to me for the value of x between 0 to L. So, this is given to me, the function is well defined for the x between 0 to L. Now, I take the case 1 and I assume that the function f x is an odd function. So, this is the assumption I am making, that I am assuming that my function is an odd function, and from here I can define my function. So, suppose my function is given to me. So, this is my 0 and this is L. So, let my f x is given to me some function of this type. So, this function is given to me. Now, I assume that this function is an odd function. So, from there to there minus L, I will extend this function from minus L to 0, and now I assume that my function, so this is my f x. So, now I assume that my function becomes f x when x belongs to 0 to L, and this is minus of f x when x belongs to minus L to 0. So, this is I have extended this function and making this function is the odd function. Now, I know that if I have a odd function, then in that case now I am able to find the Fourier series. So, my Fourier series in this case will be, so this is my function now, I call it a g x. So, this function now I am able to write the Fourier series. So, this is my g x, and odd function we know that a 0 and a n all will be 0. So, I will left with only n from 1 to infinity b n sin n pi x by L, where my b n is equal to 1 over L f x sin n pi x by L dx. So, this is I have now. Now, this function is given to me. So, I will use the property of the odd function, and this integral become 0 to L f x sin n pi x by L dx. So, now you can see that in this case I have the value of the function from 0 to L only, and I know the value of the function from only from 0 to L. This is my assumption that I am making this odd function. So, now in this case if I am taking this one, then my if I take the x lying between 0 to L, in that case my function g x is f x. So, in that case my Fourier series become this one. So, this is called the Fourier sine series. So, now it become the Fourier sine series. So, Fourier sine series when that series has contain the only sine terms, and this is possible when my function is a odd function. So, this is the Fourier sine series. Similarly, the case 2 I can take when my function f x is given to me for x belongs to 0 to L, and I am assuming that my function f x is an even function. So, in that case I have my f of minus x is equal to f x, and from here I can do the same way, I can go and then I can write my function f x is equal to a naught plus summation an cos n pi x by L, where my an is 2 by L 0 to L f x cos n pi x by L dx. So, based on this one I am able to write my an and the function f x. So, based on this one we are able to write the, so this is called the cosine series or the sine series, and we also call it the Fourier half range series, because in this case the half range is given to us. So, let us do one example. So, this is a interesting example I want to do. Suppose I have function f x and this function is given to me as sin x, and x belongs to 0 to pi. So, this is a sine function is there. Now, from here the question is that expand this one, expand f x as Fourier cosine series. So, the function is a sine, but I want to expand this one as a Fourier cosine series. It means now what I need to do, I have a function so this function is given to me. So, from this is my sine function, it is given to me pi, and I want to find the Fourier cosine series, means I have to assume that my function f x is a even function. So, what is going to happen in this case, that I am assuming that my function is look like this one. So, this is my only then this function will be the even function. So, from here I can say that we are assuming that the function f x is equal to sin x, where x belongs to 0 to pi is extended as an even function from minus pi to 0. Only then I am able to find the Fourier cosine series. So, after doing this one, now I have my cosine series. So, my f x will be a 0 plus summation n from 1 to infinity a n cos n pi x by L but in this case I am taking L is equal to pi. So, this will be pi, it will cancel out, and from here I can write my A 0 plus summation n from 1 to infinity cos n x. So, this is already given to us. Now, I want to find my A 0. So, A 0 will be 1 over 2 pi, and now what I am going to do is it is a half range series. So, I know that this is equal to 2 times 0 to pi, and f x is given to me sin x dx. So, this is given to me. So, from here I can write this is a pi and this is minus cos x 0 to pi, because the integration of sin x is minus cos x. It will be cos pi minus cos 0. So, what is the cos pi is minus 1. So, minus 1 minus 1. So, it will be 2 by pi. My a n will be 2 over pi from 0 to pi, f x is sin x, and then this cos n x dx. So, in this case, now if it is was from minus pi to pi, in that case I know that this function, using the property of orthogonality, this integral was going to be 0. But now in this case we are not taking the integration from minus pi to pi, we are taking the integration from 0 to pi. So, if I solve this one, so I can solve this integral from 0 to pi, and then if I apply the formula here, so you can apply the formula, or I can use as a first function or the second function. So, what I do is that I will use this formula, 2 sin A cos B is equal to sin A plus B plus sin A minus B. So, from here I can write that this is 2 times this one. So, I can write directly from here 0 to pi sin n plus 1 x plus sin so sin A sin B, A is x and B is n x. So, A minus B, so x minus, so 1 minus n x and then dx. So, this one I can do the direct integration. So, this 2 will cancel out because we have already used this formula, and then it will be 1 over pi and then doing the integration. So, it will be minus cos n plus 1 x divided by n plus 1, doing the integration from 0, putting the limit from 0 to pi, plus again it will be minus cos 1 minus n x divided by 1 minus n, this integration. So, from here I can write from that 1 over pi. So, this is the pi I can put here. So, minus 1 over n plus 1 cos n plus 1 pi minus cos 0 is 1. So, it will be 0, and from here I can write again minus 1 over 1 minus n cos 1 minus n pi minus 1. So, this value I am able to find. So, everything depends upon that what is the value of n. So, I can take my So, this will become 1 over pi minus 1 over n plus 1. Now, depending upon what is the value of n, if I take n is equal to 1 here, it will be cos 2 pi, cos 2 pi is 1. If I take n is equal to 2, it will be cos 3 pi, so its value will be minus 1. So, depending upon this value, if it is 1 then it will be 0, if it is minus 1 then it will be minus 2. So, depending upon that, I can write here that its value will be 0 when n is 1, 3, 5 and so on, and otherwise its value will be minus 2 when n is a even number 2, 4, 5, this one, minus 1 by 1 minus n, and again this type of value. So, if I put n is equal to 1 here, so this will be cos 0 and cos 0 is 1. So, it will be 0. When n is equal to 2 here, it will be cos pi, it will be minus 1. So, again I can write that this is 0 when n is 1, 3, 5 and so on, because if I put cos 1 minus n is same as cos n minus 1 pi, does not matter, right. So, when n is equal to 1, its value 0, n is equal to 3, it will be 2 pi is a 0, and otherwise it will value will be minus 2 when n is equal to 2, 4, 6 and so on. So, based on this one, I can write the value 1 over pi. So, this is, so I am now doing this one. So, its value will be 0 when n is equal to 1, 3, 5 and so on, otherwise its value will be, so minus minus, so it will be 2 by n plus 1, and this minus will be plus 2 by 1 minus n when n is 2, 4, 6 and so on. So, after finding this value, now from here I just make it little bit simpler. Then when n is equal to odd, but when n is equal to even, its value will be this one. So, instead of n I can put the m here, or I can write down. So, this is equal to 1 over pi 1 minus n square, this one I can take, 2 I can take as a common. So, this is 1 minus n plus 1 plus n when n is even. So, it will be 2 by pi, this will cancel out. So, it will be 2 by 1 minus n square. So, it is 4 by pi 1 minus n square, or minus 4 by pi n square minus 1 when n is even. So, from here I am able to write the Fourier cosine series. So, I can write sin x is equal to, my a0 was 2 by pi. So, it is 2 by pi plus summation n is equal to 1 to infinity. Now, I am taking n is equal to even. So, in that case it will be minus 1 by 4 minus 4 by pi n square minus 1 cos nx, but I am choosing only n is equal to even. So, n is equal to 2, 4, 6, all this value will come up, and this is, we call it the Fourier cosine series for the function sin x. So, that is obviously a new thing, that on the left hand side we have a sine function, but on the right hand side we have a cos function. So, this is the approximation of the function sin x in terms of the Fourier cosine series. So, that is the way we can do, assuming that the function on the left hand side, extended the function on the left hand side as the even function. So, after doing this one, So, this is the way we have started that for a given function, any function when the function is well defined from 0 to L, then we can write the Fourier half sine series or half cosine series. Now, we start with the next thing is that I have my Fourier series. So, I just want to write the complex form of Fourier series. So, now I have my series f x as a naught plus summation 1 to infinity. Now, I have a n n pi x by L. It is given to me. I will use this formula I x. So, this is, I know that this is equal to cos x plus I sin x. Now, from here, and also I know that the cos x can be written as E I x plus E minus I x by 2, because if I take the minus I x, minus I will come here, and also I know that the sin x can be written as E I x minus of E minus I x by 2I. So, in this case I have 2I. So, I will use this property here. So, it is to a naught plus summation a n, and this one I can write as E I. So, instead of x I have n pi x by L. So, this is there cos x plus E minus I n pi x by L by 2 plus b n now I will write it as E I n pi x by L minus of minus I by 2I. So, from here I can collect the terms. So, I will collect the terms correspond to this one. So, it becomes a n by 2 plus b n by 2I, E I n pi x by L plus a n by 2 minus b n by 2I, E minus I n pi x by L. And then this is a constant, so we can take this constant. So, from here what I do that, if you see clearly that this is just the conjugate of this one. So, from here I will write this function as a0 summation n from 1 to infinity. So, I call it as Cn E I n pi x by L plus I will call it C minus n, because instead of n I am putting the minus n, I will get the same value. So, this is n pi x by L, where I am choosing my Cn is equal to, so Cn we are choosing half a n minus I b n. So, this I am choosing. I will multiply by I here, and then this will be again this will be I here. So, this will be minus and this will be plus. So, I am taking C n like this one and C minus n like this one. So, from here if you see from here I can write this as, so this A naught I also call it as C. So, I can write this one as a new one summation n pi x by L, because from here if you see that when I take n is equal to 1 it will be n minus 1 and my 2 it will be C minus 2. So, it means the coefficient when I take n from 1 to infinity, this coefficient is going from minus 1 to minus infinity. So, it is minus 1 to minus infinity, this will be there, at 0 this A0 is there, and after n equal to infinity this is there. So, I can write this series as in the one form, that is called the complex form in this way. So, this function becomes a now summation n from minus infinity to infinity Cn this one, and where my Cn is half an minus I bn, and that will be 1 over 2L. So, an I already know. So, an is there, fx cos n pi x by L. So, I can add minus I integration. So, it is from L to L fx sin n pi x by L dx. So, this is also dx. So, if I combine this together, then from here you will see that this becomes minus L to L, and this becomes fx e raised to power minus I n pi x by L dx. So, from here I can write and that my coefficient Cn will be 1 over 2L, because 2 is coming from here, minus L to L, it will be fx e raised to power minus I n pi x by L dx. So, this is the coefficient of the complex Fourier series. So, this expression is called the Fourier cosine Fourier complex form, and this is the corresponding coefficient. So, the advantage in this case is now that whenever the function is there, I can write the function in this form, and only all the coefficients, because earlier we used to find A0, An and Bn separately, but now I can find the value of Cn together in just in one go, and based on this one we are able to write the Fourier series. So, in this way we can write the Fourier series in the complex form. So, this is we will stop here. So, this is all about that how we can extend the Fourier series into the half range series, and then we are able to write the Fourier series in the complex form. So, in the next class we will go further and study about the more about the Fourier series. So, thanks for watching. Thank you.